Hello, welcome to a BI393 Biostatistics Beyond supplementary video, where I'm going to talk about and demonstrate what confidence intervals are, what they're not, and talk about how we go about calculating them. The work we're going to be doing today is going to be working with data in the Palmer's Penguins package. Try saying that 3 times fast. And so you should make sure that you have downloaded that package from CRAN and have activated it by brought it into your active directory by using the library package. And in there, we're going to deal with the particular data set called penguins. So, and today we're also going to be using functions in 2 different packages. One's called boot and one is called car. Make sure you have both of these installed, up to date, and activated using your library function. Now, the data we're going to be focusing on today, and in this case, don't worry because we're not going to be using the logic function. This means there's just 2 packages here that both have called a function called logit, so you don't have to worry about that. The data we're going to work today is going to be on some body mass data collected on penguins, but not just all the body masses of penguins in that data frame, specifically only those that come from the Adelie penguin set. So to take a look at this data, we just would use our data frame called penguins, the variable called body mass, and then we're going to subset in here saying only when those cases where the species is equal to Adelie. So I could use my head function or my names function to see the names of all those columns, and then my levels in calling it species to find out exactly which of the options are. But let's just go ahead and say that I'm really interested in body mass of Adelies. And we can see here is the data that was collected. It was measured to the closest gram. Looking at it, though, you can see really that they measured to the closest 5 grams, which is interesting. The things they don't always say when looking at the data. And you can see that there is one missing penguin, one penguin that was part of the study that for some reason they were unable to get its body mass. Too slippery a penguin or something like that. Now, let's take a look at what that data looks like, because it's always important to plot your data before you begin. And this code here is going to sort of talk about how we go about plotting that data. So we have the histogram function, the thing we're interested in, body mass, subsetted, and subsetted using the square brackets and the double equal signs. I'm going to rotate the y-axis numbers so they are easy to read. I don't have to turn my head. I've suppressed the head, the main on the top, because that's useless. The X and Y have been given nice names with no typos. And give a nice green color, and I've been playing around with the breaks and the limitations. And let's see what it looks like. Okay, let's make that just a little bit easier for folks at home. Take a look. So let's put that down there. So a nice looking histogram that describes the data, that picks the data visually. Now there's a lot of things we might want to do with this data set. We might want to figure out what is the mean of this sample. What is the mean body mass of the Adelie penguins? And for this, I'm going to use my mean function. My data that I'm interested in is the same as before, and I've added an na.rm equals true. And I've done that because it's good practice when you're dealing with the means, because if it ever encounters an na value and this isn't true, you get a error message. There's nothing there. But if all goes well, then we see that the mean of the penguins is 3,700 grams. And I'm going to do away with the decimal places, probably referring to this, typically because this is only measured to the closest gram, and talking about to multiple decimal places kind of gives a false impression about how precise our measurements are. Now, describing the location of the mean is all well and good, but it doesn't really tell us much about the sample. It doesn't tell us about how variable the sample is. Now, we can talk about how you could use the range to look for use the min and max function to find out which the biggest and smallest penguins are, and sort of talk about that range. But that also doesn't really capture much of the essence of this distribution. So there's a bunch of different ways that we can describe that variation. The first one is that of variance. And in variance, we are essentially looking at how much variation there is around the mean. Where if there's lots of variation, you get very large numbers. If they're all tightly close together, then you get a very small value. Variance is easily calculated in R using the exact same structure as before. But using var. Now, this var value of 210,282 is not that great to use because of the formula for making variance involves sort of squaring the units. So this variance is measured not in grams, but in grams squared, which is not something that you or I or most people would really understand much about. So instead of using variance, we typically take the square root of the variance to get the standard deviation. And the standard deviation is calculated with the function SD, and the value that we get from here, 458, is in grams. So this gives us some measure of the amount of variation that we see in our sample. Now, we may want to combine our questions about variation and our interest in the location of the mean to get a feeling for how well are we doing an estimate of the mean. Remember, that mean is an estimate, it's a parameter, and something that we have estimated based on the sample that we have. Now, how do we go about figuring out about how much uncertainty or how good or how accurate, how meaningful is our estimate of the mean? Well, this is where confidence intervals come in, because confidence intervals tell us something about the degree of uncertainty associated with our estimate of the mean. Now, to estimate the confidence interval, there's a bunch of different ways we can do this. The first thing we're going to need to do is we're going to estimate our sample size. And we could do this manually. I could scroll up here and count them out for 144, 45, 46, 47, 48, 49, 50, 51, 52. But then remember, oh, there's one missing. It's 151. Or I could use the length function. And the length function tells you the length of whatever you put into it. But it does not discriminate between a value that is NA and a value that is 4,000. It would count them both as 2. And really, our sample size should include only the ones that we actually have data. So I have taken our penguin's body mass, subsetted by Adelie penguins, and I have nested that inside the function na.omit, which says omit any NA values. And then I've taken that and nested that inside the function called length, which tells me the absolute number of individuals in that line. And, just as I said, 151. Now, we need this to calculate this for a couple reasons. One, so we can estimate degrees of freedom later on, but also because if we want to get an idea about the uncertainty of the mean, we have to calculate the standard error of the mean. And there is no built-in standard error function in R, but that shouldn't stop us because we can write our own. And we can do so by creating a function. So here I'm this whole new function called standard SD error, and I'm using this function called function to say that I'm going to be writing a function. Pretty imaginative stuff. And the next column, the next line, I'm going to write what the formula that I want this function to do. And this is the formula by which we calculate the standard error. That whatever set of data we put in here for x, that we're going to take the standard deviation of that and divide it through by the square root of the number of measurements. So the length in AO mid of x. And we hit enter. Everything looks like it's good. So we are good to go. And I can plug in the thing I'm interested in. Penguin body mass. So what's my standard error of the mean? It is 37.3, which is pretty cool. Now, with that value, we can now calculate the confidence intervals, the 95% confidence by hand, using the formula where we take the mean value and we take and we either add or subtract to that value the product of the standard error of the mean, which we just calculated, and the t-statistic. And the t-statistic is a term which is used to describe the distribution of points around a mean that when we have sample sizes that are relatively small. If we had a very large normally distributed data, you would expect that 95% of all of the data points would fall between 1.196 plus or minus standard deviations from the mean. That's not the case if we have small sample numbers because of stochasticity, of randomness of those particular elements. And so student, which is a pseudonym, we're going to talk all about him and his exciting life later on in this class, figured out and calculated t-statistics, which essentially are corrections for small sizes. Now, we could go into our Fowler and check students' t-tables to get an approximate t-value based on our degrees of freedom based on our sample size, or we could just ask R to give it to us instead. And so for R, we ask the function qt, quantile of the t-distribution, and since we're interested in what's called the 95% confidence interval, we want to have 5% divided amongst the two tails. So 2.5% on one side, 2.5% on the other. So to get the first t-statistic, we go at the 2.5% level, and the argument we put in here is our degrees of freedom. And that is, in this case, 1 less than our sample size. And it's 1 less because we've had to sacrifice 1 degree of freedom to calculate, estimate the mean. So that value gives us a value of minus 1.975, so close to 1.96. But, you know, 150 degrees of freedom is not infinite. It's, you know, quite finite. And we get the other one at the 97.5 percentile, and same magnitude, same size, different sign. So now we can just sort of plug those things in together. So we would take our mean value, which is 3,700, and then we're going to say start by getting our upper confidence interval. We're going to add the t-statistic times the standard error. It's right there. And this tells us our upper confidence value is at 3,774. If we want to get our lower confidence interval, we put in negative values. And so that's 3,626. So let's look at this graphically. I'm going to add in an AB line. And I want to add a vertical line, so with V, and I want to put in my mean value, because that's a good place to start. So put a vertical value at a line at 3,706, and that's right here. And if I want to show the 95% confidence interval, I can put my lower confidence interval, my upper confidence interval, and I would put line type 2, just to make it easy to see, and my other one, which is 3,076. So you can see the black line here at the center is our mean, and the 95% confidence interval refers to the confidence interval around that, which tells us the sort of idea about the precision by which we can actually sort of estimate that mean. Now we can calculate confidence intervals by hand, but R has lots of handy-dandy tools in them that allow us to sort of take shortcuts. One of which is using the t-test function, which we're going to talk a lot and use a lot in this class under some situations. For right now, we're going to ignore all the hypothesis testing parts of the t-test function and focus just on the t-test values. And the as you can sort of see, that it has our sample at mean, which is the same. And you'll notice its 95% confidence intervals are the same as what I calculated by hand. So saved a lot of time. Ignore all the rest of that. We're going to talk about that later on. The important thing to remember, and this is where people get confused, is that when we're talking about confidence intervals, we're not talking about the specific parameter we're estimating. And we're not talking about the mean of 3,700. We're talking about the sampling process that produced that estimate. So with what was the process by which we were able to estimate that mean? Did we do it with a great amount of variation, or was it fairly consistent? Now, to illustrate what I'm talking about, I want to give some graphical illustrations, and I'm going to imagine that we're going to do this study 100 times, because strictly speaking, the 95% confidence interval refers to the idea that if we were to resample the population from which these penguins came from 100 times, that a confidence interval using this process would capture the true mean 95% of the times. Now, we're going to do something which, strictly speaking, we shouldn't be able to do. That we're going to go back and imagine that we could do this study 100 times. We don't have the time or the money or the penguins to do this, but we can imagine we can in the world of R, just to illustrate this. So we're going to imagine that we're going to do this 100 times. And we're going to imagine that we could have some information about the population itself. So what is the population? We're going to imagine that this population, the hypothetical real population, not the sample that we have here, has the same properties as our sample. So we imagine that we have has a mean of 3,700 grams, and its standard deviation is 458 grams. And we're going to, with these values, we're going to imagine that we could create an imaginary population of penguins. So 10,000 in size. Now, what does this population look like? Well, let's look at a histogram of the imaginary population, shall we? So here's our population, there's our imaginary population. Now, the mean of our imaginary population is 3,703, and we had created this using the rnorm function, the random norm function, to imagine that we were creating one from a population that had those values. And so it's pretty close. There's going to be a little bit of sampling error. Even with 10,000 individuals, you have a little bit of randomness happening here. And I'm just going to save that mean value for later on. So I'm just going to assign that to an object called pop.mean. Now, from this imaginary population, I am going to imagine that I took a sample, a sample of, say, 10 individual penguins. So I'm going to take my function called sample. My imaginary population is the data frame I'm sampling from, and I want to calculate a value to take only 10 individuals. So I do my random sample, and I take a sample of that, and I take its mean. And in this case, my sample mean is 3,781. When you do this, you're going to get a different number because you are randomly picking 10 of all those 10,000 penguins. By chance, you might have had a few penguins that were heavier, a few penguins that were lighter, or maybe you might have ones that are very close. And with this data set, I can do the same things I did before. I can calculate the 95% confidence intervals of that sample, and then you see there's nice symmetrical ones. There's my mean, there's my confidence intervals. Now, imagine what I want to do is if I wanted to sample this 100 times. And for each one of these, I wanted to look at those confidence intervals. So I'm going to need to create a new function that's going to be able to do that. So I'm going to make a new function. It's called getConfInt. And it's a function as before, and all it's going to do is whatever value I put inside the function, I'm going to take a t-test, a one-sample t-test, and extract the confidence interval values, whatever is found in that particular row. Now, I'm going to need to create some data, and I'm going to, instead of sampling just one at a time, I'm going to make 100 samples at a time. So I'm going to sample my imaginary population. I'm going to take 100 samples of 10 with replacement, so that every time I take it out as if the numbers go back into the bin. And then I'm going to take those numbers and I'm going to feed them into a matrix, and that matrix is only going to have each of those groups divided into groups of 10. Now, I'm also interested in sort of thinking about what happens with my sample size. It's going to be important later on. I'm going to do the exact same thing, exact same code, except that I'm going to sample 50 penguins at a time instead of 10 penguins at a time. Now, with my data, I'm going to take the object, which is called draws10, and I am going to apply, which is a really cool family of functions. It's going to apply the function that says get confidence interval to the data set working down by columns. That's what the 2 indicates. So what it's going to do is that it is going to, in the blink of an eye, look at each column of 10 individual penguins, run it through a t-test, extract the 95% confidence intervals, and save them in a new object called confintervals10. So I hit enter. It's done it. Amazing. R can be very fast. And I'm going to do the same thing here with my samples of 50. Now, remember I said that a 95% confidence interval means that it refers to the likelihood that if we resampled the population the same time 100 times, that 95% of the time it would contain the true population mean. Well, we can actually test that. So I can take my confidence intervals and ask in the upper and lower columns, how many times is my mu, my actual sample mean that we had before, how many times does it actually inside that confidence interval and how times it out. So in this particular case, it was successful at getting them 98 times. 95% is an average. Now let's do the same thing here for the 50 samples. And when you do this, you're going to probably get different numbers than 98. Here I got 96. So interesting things. But this doesn't really graphically represent what I'm sort of wanting to talk about. So I'm going to do some plotting, and I'm going to plot two different plots at the same time. So I'm going to change the parameters. Par mf call equals c1, 2 tells me that I'm going to be now plotting on two things into one window. So we're going to start off by plotting an empty plot. So I'm going to use the range for my x values, from 1 to 100 on my y values. It's a type n, which means don't plot any points in here. I've made a nice x labels and y labels, and I've rotated those numbers there. So it should look nice. And into here, I now want to draw in all my individual confidence lines. So I'm going to take the number of the values within from sample 1 to sample 100, and I want to just plot nice horizontal lines that represent those confidence intervals. And the other thing I want to do now is I also want to put in a vertical line that shows where the hypothetical true population, the true population means. And as you can see here, I make this nice and big, that of the 100 trials that we did, only 2 of them missed. So if the red line and the black line intersects, it means that the true mean was captured inside that confidence interval. Only 2 times it wasn't. But what about that other sample I did of 50? Well, let's take a look at what happens if I plot those 50s. Do the same thing here. And what you'll notice is that when the sample, in our second sample, if you remember that we had, how many was it? 96. Where are the 4? 1, 2, 3, 4 of them missed it. But you'll notice that when I only sampled 10 penguins, there's a lot more uncertainty associated with my estimate of the mean. Well, in comparison, when I have a much larger sample size, I have a much greater ability to more accurately estimate the means. And so as that's reflected in smaller confidence intervals. So confidence intervals don't tell us about the specific parameter that we're estimating. Each one of these samples has a different mean. So the confidence interval doesn't refer to those specific parameters. It talks about the capacity of our sampling process to and how much uncertainty is associated with it. Bigger sample sizes, less uncertainty because we're able to estimate the mean more accurately. We're much less impacted by small stochastic events. 10 penguins, 1 super big penguin will throw the whole thing off. In 50, 1 super big penguin won't have as big an impact. So confidence intervals, that sort of talks a bit about confidence intervals. Now, one thing that is a little bit frustrating about all of this is that we don't have the capacity to go back and resample and go back and collect 10,000, from a sample of 10,000, do a study 100 times. We are limited by the data that we have. So a different approach to thinking about and estimating confidence intervals relies upon the process called bootstrapping. And bootstrapping is a process of resampling with replacement. That we have our 151 penguins in here, and this is the best estimate we have of the large population. So instead of imagining a hypothetical population, we are going to repeatedly sample this particular population. So let's make this small again. And for this, we're going to use the package functions in the boot library. So already loaded that up before, but just as a reminder for later. Now, when we're making a bootstrap, we need to do a couple things. We need to have a particular function that we're going to apply. And in this particular case, I'm going to make a function called mean function that is really not going to do much of anything different than we've seen before. It's going to calculate the mean of a particular group of data, but I just wanted to make sure that the default na.rm equals true is in there, so we don't get messed up by that one na value that might get picked up several times. So with that in place, I'm all set to start bootstrapping my data, sampling from my data frame and calculating mean values. So I'm going to make a new object called boot distribution. The function is called boot. There's the data that I'm sampling from. The test statistic I'm using is my mean function. And I want to do 10,000 samples. So 10,000 samples, 10,000 means. And as you can see, I hit enter. It's done in just like a second or so. Crazy. Now, if we were to look inside this particular data frame we just created, there's a column called T, and it is we use the head function to look at the top 6 rows, because if you just wrote boot this $T, you'd get 10,000 rows filling up your screen, and that takes a lot of space and time and patience. So we have 10,000 values. And if we look at the mean of those values there, it is 3,701, so pretty close to what our sample mean was. And that makes sense because they are sampling from our population 10,000 times. So it's by the central limit theory, it's going to be pretty much the same. And the other thing that's very fascinating about this is that if we take the standard deviation, that the standard deviation is pretty much the same as the standard error of the mean, and that's because it is the standard deviation of the sampling distribution. Each one of these is a mean, and the standard deviation of all these means is essentially the same as the standard error. So let's take a look at this just to make clear we understand what we're talking about. So here is our original penguins data. And what we're looking at aren't individual penguins. We have 10,000 estimates of the mean values. So I'm going to do the same thing. I'm just going to have my bootstrapped. Let's not have some typos in here. The bootstrap mean masses. The number of bootstrap values, and I'm going to estimate that, hit enter, and you can see here, this gives you the individual values that we have here on that same initial scale. Now, whereas our previous one had values of very small, really large, and I'm just going to zoom in a bit. I'm just going to change the limits just to make this a little bit easier for everybody to sort of see. So these are various estimates of the mean. So these are not the original penguins. These are the samples, the bootstrap samples. Now, with this number, we can get confidence intervals in several different ways. We can calculate the 95% confidence intervals by hand. We can use the theoretical underpinnings that If we want to get the 95% confidence of the mean, that here are a whole bunch of different mean values, and we can look at the 95% values. So look at the lower level, at the 2.5% and the 97.5% levels, and we can do that here using the quantile function, and this gives us quantile values here. And we can also do this the way we did before, where we take the mean value plus and minus the t-statistic and multiply by the standard error, which in this case is the standard deviation of the sampling distribution. And we can get our t values by plugging the value. Here now our degrees of freedom is 9,999. Because we had 10,000, and we have to estimate one thing, the mean. And you can see here that as our sample size is getting very large, we are getting really close to that hypothetical 1.96 value. So we're pretty close to what's considered a large sample size. And I could plug these things in before. Now, the final thing that we might do is a slightly different approach, and this is going to use in the library car. It's going to use the function conf interval. We've already loaded library car in, and what this is going to do is going to do a corrected bootstrap bias corrected confidence intervals, which is going to take into account what the sample mean is and if there's any degree of skewness happening in a sample. Now you'll notice these values are pretty close to each other. They all have slightly different assumptions about things, but I wanted to show you sort of the different tools and techniques that we had available. I hope this is helpful and that you enter into the world of confidence intervals with a bit more confidence. Have a great evening, and I will see you in class. Take care. Bye.